In this fourth guided review problem for shear and moment diagrams, we have again a simply supported beam that has, in this case, a distributed load that goes over the entire length, but we also have two end couples. Right? We have 20-foot span, 100 pounds per foot for distributed load. That magnitude is probably pretty similar to the self-weight of the beam. And then we have two end couples coming from other portions of the structure that we don't see here. And these reactions are probably columns supporting this thing, so at 800 pounds and 1,200 pounds. So let's take a look at the shear diagram. We start off at 0. We have that concentrated force of 800. That takes us up immediately to a net of positive 800 pounds, and then we have a, oh wait a minute, dV dx equals q. So we do have a distributed load. It is downward, so therefore negative. So we have a negative slope, and it'll be a constant negative slope. And so the total change will be this, all of this area. So 100 pounds per foot times 20 feet will be 2,000 pounds, so 800 minus 2,000 would be a minus 1,200. In straight line variation, get to our net of minus 1,200. I have a little wiggle right here so that nobody thinks that I'm trying to do something funky here. I'll just put a first order curve there. I guess I wasn't able to really draw a straight line, even with a straight edge. And then, of course, we need to close off to 0, and that 1,200 pound reaction does that for us. On the moment diagram, we start off at a 3,000 foot-pounds. However, it is going frowny face here, so counterclockwise moments cause a negative discontinuity in the moment diagram. We immediately go down to this minus 3,000. And then let's see, we're going to then increase the moment because dm dx equals v. We have a positive slope here. We have some sort of a local peak. We don't know how big that is. We need to find out that location. And let's see, this is 800 pounds going down at 100 pounds per foot, so that would make that 8 feet. And so this area will be 1/2 of 800 times 8. So there's 6,400, that equals 3,200. So it looks to me like at 8 feet over, then we have a negative 3,000 plus 3,200. We end up at a positive 200 foot-pounds. And then we've got 12 feet here, and that area will be 1/2 of 12 times 1,200. So that will be 12 divided by 2, that's 6. That will be 6 times 1,200 would equal 7,200. So we're going to go, oh, hey, that works out. Start off at 200, subtract off 7,200. We're going to end up at a net of negative 7,000. And we had that end reaction, which was frowny face. And so that was a clockwise moment, and that would cause a positive discontinuity. So I think this is going to work out just fine. Just kind of change my colors here on you. But now what we have to do is get a second order curve to fit in here. We don't have to have it perfect. We just like to try to make it so that where we have 0 slope, which would be 0 shear, that would actually be reasonably close. So I'm going to have a hard time getting that to do it there, so I'll try a different portion of the French curve. Getting better, better, better. Okay. Now, it probably is not true that I've ended up with the 0 moment being right where it's supposed to be. So I'm not going to scale that location, but I'm not going to get too concerned about it. if I really care where that moment is 0 at, I'm going to use math to figure it out. I'm going to lay out that French curve as best I can. I really like to mirror what's going on, what I have over here to the left, because I have the same variation in shear, so therefore the same change in slope. But there again, it's hard to get French curves to match up perfectly. This is more notional than it is to be taken literally in a scaled kind of fashion. But that's another reason why you want to make sure that you indicate that you got second order curve and you got the critical values marked, so that people understand what it is that you intend, even if it's drawn just a little bit different than it might actually need to be if it were scaled.